Hello, this video is going to be an introduction to magnetic fields and the Lorentz force, specifically the magnetic component of the Lorentz force. So when we have a permanent magnet that most people are familiar with, you have a north and a south side, and these directions are kind of determined arbitrarily. So like if we have a north and a south bar magnet, um, all magnets will have two poles at least. So you have to have a north and a south. You can't have a monopole. Um, but if you have like a magnet with north and south here, we'll label this one the blue side north and the south as red. You can draw magnetic field lines for the magnet similarly to how you draw electric field lines for say like a point charge. But again, like I said, you can't have like a monopole, magnetic monopole like you can have like an electric monopole. So for example, so all of these will have a north and a south. But for magnets, the magnetic field goes from north to south outside of the magnet. And so if we were to draw the magnetic field, we would have like field lines going out of the North Pole and into the South Pole, and then you'd have some field lines that like curve, so they form loops of various sizes. And so these field lines, again, they point out of the North Pole and into the South Pole. All right, and then let's see. Inside of the magnet, these field lines will just continue. So you would have like these field lines here that go from south to north then. But outside of the magnet, um, these field lines go from north to south, and inside of the magnet, the field lines go from south to north. And field lines, just like electric field lines, they don't cross. Um, and so whenever you have like two magnets that are together and you have field lines that like would seem like they would intersect, you can use the principle of superposition to add the magnetic field at those points together and get a resultant field. So like for a single magnet, it might look something like this. But like if you had two magnets, like let's just say they were if you're going to repel, so like repels like for magnets basically. If you have like two south poles of magnets, I'm just omitting the north poles of these magnets here. The field lines would go something like, just like if you had two charges of the same sign, um, the field lines they wouldn't intersect and they wouldn't connect to each other because they're both going they're parallel in the same direction basically at like these points. So they would go again into the South Pole, but then since they repel, uh, these field lines again they don't cross. You would just superimpose them against each other. So like if I were to draw this with field lines that did cross, so like if I were to overlay the field lines for each of these together, like for the left side, the field lines would look something like this. I'll just draw it like that. So it goes like that direction into the magnet, and then for the right side, it'll just be a mirrored copy of it. So it looks something like this. Again, and these go um, into the magnet, into the South Pole, since they're external. And now, like if we look at like this point right here, you have one field vector going in the right direction, and then you have the other one going in the left. So the net magnetic field at this point is 0. That's why you see at this point there's no magnetic field. But then if we were to look at like a point like right here, you have one vector pointing down here and one vector pointing down in the other direction. So the net vector is going to be pointing directly downward, which is why the net vector right here points directly downward as well. So these follow the principle of superposition. And then I'll draw an example of like a south and a north pole. Basically, it's like the same thing as like if you had two oppositely charged particles, where you basically just have like field lines that go from north to south here um, in the external magnetic field, and then um, this would look like the edge of a capacitor almost, where you have like edge or fringe vex where it like starts bulging out because its magnetic field is closer to uniform, or it's close to uniform as you get to the center and as the distance between the north and south poles decreases. So if they're close together um, relative to their size, then this field here seems uniform, but then as you get towards the edge, it starts curving outwards more. But again, um, if you have two opposite poles, these field lines connect like this and they attract. But if you have the same poles, the field lines seem to repel each other or push each other apart. Uh, right, now we'll get into how magnetic fields are created or formed. So, magnetic fields form as a result of moving charges. And so whenever you have like a charged particle or whenever you have like a current running through something, that induces a magnetic field around it. So that creates a magnetic field around the moving charge. And so if you have a wire here, like if you have a rod, or like this is a metal wire, let's say, and then you have some current going through this wire, let's just say in the upward direction, uh, it'll induce a magnetic field into it. So there will be a magnetic field around this wire. And the magnetic field, the direction of the magnetic field follows the right hand rule. And so what the right hand rule states is that if you have like your hand here, and then, uh, so if you use your right hand and you curl it up into a fit like a thumbs up position, the thumb like so where you like stick your thumb out and then you curl your fingers um, into like so you curl your fingers and then stick your thumb out. So like if this is your right hand, then your thumb, if your thumb points in the direction of the current, so if this is where the current, and then this is conventional current, so it's the direction of positive charge flow. So like if this was the positive end and this was negative end, um, like or the if for this scenario where the current is upwards, you would have like the positive end of the wire here and the negative end of the wire on the other side. And then current flows from positive to negative. So this is not electron flow. This is conventional current or the direction of positive charge movement. So if current goes in the direction of your thumb, then the direction your fingers curl indicates the magnetic field. So in this way, you see your fingers curl like that. Um, so if your fingers curl, um, the way your fingers curl is the same way that the magnetic field forms. So if you have a current traveling through a straight wire, they'll create a circular magnetic field that like goes around the wire in this direction. So that's the way that your fingers on your right hand would curl if your thumb was sticking in the direction of the current. Um, and now it's really difficult to draw 3D like these 3D fields in a 2D space because like electricity and magnetism, well, especially magnetism, like in this case is inherently three-dimensional. And so to draw this, we won't draw like these loops here, like we do. We'll have like, let's just say we have a wire here, and then we have some current running through it. Um, if we look in the plane, if we look at a slice of this wire, like a plane of it, then we see that at like this point, or if we take a plane at this point, um, the magnetic field is going into the plane. So it's pointing into the plane, which means that we can represent it, if we represent it as an X, that's the standard like symbol for pointing into the plane. So since the magnetic field is going from like outside of the plane into the plane, then we'll represent it as x's. And you can think of this as like, I've seen it said where it's like the x looks like the head of a screw. And so if you're screwing something in, then you see the head of the screw where it's an X. Or you can see it as the tail of an arrow. So like if you have an arrow here, and the arrow is moving in this direction, then when you look at the tail end of it, it'll look like an X. And so if you see the X, it means that it's going away from you, basically, or into the plane. Now on the other side of it, you see that this magnetic field is pointing out of the plane. And so we'll represent the field pointing out of the plane um, with, uh, we'll represent it with a dot. So again, if we're thinking about like a screw here, or like a Phillips head screw, there's an X there, and then this is a pointed tip, or like an arrow. The tip of the arrow is a point. And so if a field is going out of the page, or a vector is going out of the page, we can represent it with a dot. And then if it's going into the page, we'll represent it with a cross. And so this is a way we can represent how the magnetic field around a wire looks, to where, following the right hand rule, this wire has a circular magnetic field around it, where it goes into the page on the right side and out of the page on the left side. Alright, now we'll find a formula for the strength of the magnetic field around a wire. And so magnetic field strength has the variable B. So B with a vector, this is the magnetic field vector, or like, so this is magnetic field. And so magnetic field strength would just be the magnitude of this vector. So if we want to find magnetic field strength, we can do, there's something called Ampere's law, which requires calculus, but basically it says that. So we have Ampere's law. And what this states is that if you take the path integral, of B dotted with dl, where L is your path, around some current carrying wire, then you can, or like around some current, then this is equal to mu 0 I, where mu 0 is I think mu 0 is the permeability of space, and I is the current. Alright, so again, the integral, this is the line integral around a closed line or closed path of B dl dot dl, so B dotted with dl is equal to vacuum permeability times current. And so what does that look like? Well, if we have a current carrying wire here, and so we have like a wire, and then there's a current I going through it, we can choose a path, like a circular path here, and we'll say the circular path, or a circular line here, this curve, has radius r. Let me do this in a different color. So this has radius r from the wire, and this is a circle. So now, given that it's a circle, we know that it's symmetric, and since the magnetic field is symmetric, we expect the B magnetic field magnitude of B to be the same at all points, which means that we can treat it as a constant. And so basically what we get is this integral becomes B just dl, and then this is equal to mu naught I. Now dl here, this length, it goes from 0 to 2 pi r, because that's the circumference of this circular path, and so that's the length, the path length of this curve. And so what we get for this integral is just b 2 pi r is equal to mu naught I. And then so for finding magnetic field strength around a wire, as a straight wire current carrying, when we get that B is equal to mu naught I divided by 2 pi r. So this is a really useful equation because you can get the magnetic field strength around a wire at a certain radius. R, it's lowercase r I put it, but it's like the same thing basically. So it's the magnetic field strength at a radius from a wire. And an easy way to remember this is that magnetic fields form circular, well, it's a circular field around a straight wire, and then you have mu naught I divided by 2 pi r, which is the circumference of a circle. Okay, now another case where we can apply the right-hand rule that's really common is with wire loops. So let's just say we have a loop of wire that looks like this, and then we have some current like going through in this direction, like through the loop. So this is current. Now if we apply the right-hand rule at all points throughout this wire, we'll see that this magnetic field is going to be going, again, it's going to be going out of the page at outside of this loop if you use the right-hand rule, because the current is going up or through the loop clockwise like this, and it's going to go into the page inside of this loop. And so if we look at the magnetic field around this loop, it's going to be out of the page, outside of the loop, and then into the page inside of this loop. And so there will be a concentrated magnetic field that's going through the inside of the loop. In this case, since the loop is the current is going clockwise to the loop, the magnetic field is going to be going into the loop. And then if you notice that if normally we have right-hand rule where we set the direction of the thumb in the in the same direction as the current, and we set the fingers, the curl of fingers, to the direction of the magnetic field. But if we set the magnetic field, so if we set the magnetic field direction as the thumb and the curl of the fingers as the current inside a loop, then this becomes, it also works out. So we have like almost like a reverse right-hand rule type of thing, where if we have again our right hand here, and so this is our right hand, and then if we set this thumb to be, or in this case we usually use this when we want to find the direction of a magnetic field in a loop. We see that if these fingers curl in this direction, which is the current, so if the current is in the direction that the fingers curl in, then the magnetic field, the direction of the magnetic field inside of the loop, is going to be the direction of the thumb. So this is inside of the loop. Alright, and then another thing to notice is that if we have like multiple loops, so I'll draw them like this, or that might look confusing, I'll draw them a bit. So like if we have multiple loops like that, the current through them is in the same direction for each of the loops. So the effect of the magnetic field inside of them gets like added together. So then you have a magnetic field that's going into the loop here. I'm drawing this in 3 dimensions, but like you have a magnetic field that's going into the loop, and the magnitude of this magnetic field is going to be amplified because there are essentially 3 separate loops that are adding together to form this magnetic field. And so magnetic field will look something like this, where it's like it's into loop still. So it looks the same as for a single loop, except it's just greater in magnitude. And so if the loops, if there's multiple loops or turns inside a loop, then the effect of the magnetic field gets amplified. Okay, now we will go over the Lorentz force. And this is incredibly important. So the Lorentz force describes the force on a charge due to uh, electromagnetic fields. So we've already covered basically the electric field effect of the Lorentz force, because let's see, the Lorentz force is equal to, um, so we have F is equal to the charge Q times E, which is the electric field, plus V cross B, which is the magnetic field. Okay, so this is the Lorentz force. Now, the E section of it is the electric field again, which we have covered in electrostatics. The section we're interested in right now, this is magnetic. The force from the magnetic field is equal to, so if we write Fm, this is equal to QV cross B. Alright, and what the cross product means is that the magnitude of this vector, because this is a force is a vector here, magnitude of this magnetic force vector is equal to QVB sine theta, where theta is the angle between the two vectors. And so like let's just say this is V and this is B, then this would be theta. One thing to note is that the cross product, this force, is going to be perpendicular to both these vectors because of how the cross product works. And in a right-handed coordinate system that we usually use, the cross product is going to be right-handed, which means that if you use your right hand and you start with your fingers pointed, or you start with your, if you start with your fingers pointed in the direction of V, and then curl them towards B, then the way your thumb is pointing is going to be the way F is pointing. So like if we have V here and B here, so like V and B, in order for your fingers to be able to curl from V to B, your thumb has to be pointing out of the page in this scenario. So the force here would have to be out of the page. And then using the property of this cross product, and so I'm going to box this is really important. The property of cross product, we can use the right hand rule for cross products, or we can use a left hand rule for the Lorentz force, which is, so this is the left hand rule. So left hand rule. And this is where if you use your fingers, the fingers of your left hand, formed in like almost a gun-shaped pattern, where it's like you have your middle finger pointed outwards like this, your index finger pointed. So if these are all 90 degrees from each other, so like they form like almost a coordinate axis. So these would be like, this would be like your left hand here. Sorry for the crude drawing, but if this was your left hand, and then these are at like 90-degree angles from each other, and then these are mutually also at 90-degree angles, then you can label these as like this is a gun, or it looks like a gun, so you can label it as F, B, and I. So F is the direction of the force, B is the direction of the magnetic field, and then I is the direction of current, or the direction that the charge is moving in. And so if you have a current moving through a magnetic field, then the force on that current carrying object, or on the charge moving, is going to be in the direction of the thumb. And so this B is from north to south. So it's in the same direction as the arrows on like these magnetic field lines. So up here, like B here would be, if we're looking at the left side of this, it would be to the left. Or like in this whole picture, on like over here and here it'd be to the left, but over here it'd be to the right, since it follows the same direction as the field lines. So your force, the magnetic force, is going to be in the direction of FBI, or it'll follow FBI. or the left hand rule. Okay, so we've covered, so like for an example, if we have like a magnetic field that's going like in this direction, like so downwards into the page. So this is your magnetic field. And then you have a charge here, like a positive charge, uh, moving with velocity v to the right here. So this is v. Then you see that if you orient the left pointer finger downwards to match the magnetic field, and you orient your middle finger I or V in the direction of the velocity of this positive particle, then your thumb ends up pointing into the page. So the force on this is then into the page here. So the force is going to be into the page or into the plane. And now again, force always has to be perpendicular to B and I. But B and I or B and V do not have to be perpendicular to each other. And so like if you had a velocity here that was like going in like this direction, the force would still be going into the page. It would just be smaller because you have a sine theta that scales the force downwards. And then another thing to know is that if you have a negative charge instead, then the charge is negative. So your Q here is negative, and that flips the direction of the force because this is a vector. So if Q is negative, then this direction of the force flips. Or you can think of it like the current flips in the opposite direction since it's a negative charge instead of a positive charge. So that means that instead of into the page like the positive charge, this negative charge would experience a force out of the page. So this is the force in the negative charge. And finally, if you have any charge that's moving parallel to B, then you know that sine theta here is equal to 0, which means that the force is 0. So if the charge is moving parallel to the direction of the magnetic field, then the force on it, the magnetic force from the Lorentz force, is going to be 0. Okay, so now we have this equation here, Fm is equal to QV cross B, for the Lorentz force on a charged particle, but we also can easily derive the equation for the Lorentz force on a wire, a current carrying wire. So like if we had a wire here, and then we had some current running through this wire, so like let's just say in this direction, and then there was a magnetic field. So if the wire was in a magnetic field, let's just say it's going out of the page. So this is like a uniform magnetic field going out of the page. Then what direction is the force in? Well, first of all, we see that the current is perpendicular to this magnetic field, so there has to be a force. Using this right hand rule, orient again middle finger in the direction of the current and pointer finger in the direction of the magnetic field, which is into the page, we see that the force here is going to be to the right. And so this is going to be the force on this wire. Now, how do we calculate the magnitude of the force on the wire? Well, let's see. So now we have, let's model this wire here. This wire is going to have a length L, and it's going to have charges here running through it. So like, let's just draw, for example, it's going to have various charges going through the wire at velocity v. So we'll assume these charges have constant velocity throughout it because we're assuming like constant current for now. And then again, if we take like the limit as time approaches 0, we can like treat all currents as basically temporarily constant almost, or linear. So if we look at this, then the total charge of these particles, let's call it Q. So that's the total charge of the particle. So we have F. So the total force on this wire is going to be F is equal to Q, which is the total charge. So all the charges inside the wire right now, times V, and then cross B. So cross B. Now V here, the velocity of this, well, we can determine the velocity of this with its relation to current. So if there's a current I passing through the wire, that means that there are Q charges passing through the wire in a certain time interval. And so for all of these charges inside the wire Q to pass through the wire, it would take the time it takes for the bottommost charge to travel all the way to the top. Because if the bottommost charge travels all the way to the top, that means that every charge above it will have passed through the wire in that time interval. So the time interval it takes for the bottom charge to travel all the way to the top is equal to, so this time is equal to L divided by V, which is the velocity of this charge. So in L over V time units, if a charge at the very bottom of the wire will be able to travel all the way to the top, and then this means that the current through the wire is equal to Q, which is all the charge currently in the wire, divided by the time it takes for all of those charges that were initially in the wire to exit the wire, so to pass through a cross-sectional area, which is the definition of current. And so if we plug this in, we get I is equal to QV over L. And then solving for V, we get V is equal to IL over Q. And so if we plug V into this equation now, we get that Fm is equal to Q, or Q times IL over Q cross B. And then this is equal to, so we have Fm is equal to IL cross B. Here L is going to be the vector, and so for the original Lorentz force equation, V is a vector because that's velocity, and B is a vector because that's a magnetic field vector. But for this new one, we have L as a vector, so L is the direction. It's the direction of the or it's the orientation of the wire, and it's to where in the direction of the positive current. So like for this wire here, the L vector would be in this direction, and then it would have a magnitude of the length of the wire, and the I is just the magnitude of positive current you can think of. And so this equation here, Fm is equal to IL cross B, is going to be the force, the magnitude of, or it's going to be the magnetic force on a wire carrying current. So this and these two equations both describe Lorentz force. Now, let's look at some applications of the Lorentz force. So let's imagine that we have, let's say we have a constant magnetic or a uniform magnetic field here going into the page. And then we have a charged particle that gets shot through this wire. So let's just say we have a proton here, or a positive charge that gets shot through this wire here. And then we'll also have a negative charge that gets shot through the wire. Or through, not the wire. Both charges get shot through the this magnetic field. And so these have original velocities v here. What now we can ask, what are the trajectories of these particles? Well, we know that using the left-hand rule or the right-hand cross product rule, we know that since the magnetic field is into the page and the velocity is upwards for this left particle, the positive one, the magnetic force on it is going to be in the left. So the force is to the left. And so that means that this particle will trace out a path in a circle, like a semi or in a circular arc, because this force is always going to be perpendicular to velocity, and it's always going to be to the left of velocity if we look at it in this orientation. Now for this negative particle, since it's negative, we know the force is going to be in the opposite direction of the charged particle, or the positively charged particle. So the force is going to be to the right of velocity, and we're looking in this orientation. So it'll travel in a semicircular arc to the right here. And so those are the paths of these charged particles in a magnetic field. And looking at another example of this, let's just say we have a uniform field here, again, going into the page. If this was out of the page, then you would just flip the directions kind of, because again, you just have to follow the left-hand rule or the cross product rule for determining the direction of the force. Let's just say we have a particle here, positive here, to make it easier. Start out with an initial velocity um, like v in towards the left. That means that the force is going to be perpendicular again. So like if we're using this, we'll see that the force is going to be inwards here. But after this particle has traveled a little bit, let's just say to here, um, this velocity is going to be in this direction, and the force is still going to be 90 degrees perpendicular to it. So we'll see that as the particle travels, the force is always perpendicular, and that means that since the force is perpendicular, the acceleration of the particle is only perpendicular to the velocity, and that means that it's in circular motion. So again, that means if the force is always perpendicular, then the particle has to be accelerating in centripetal acceleration or circular motion. So basically what we get from that is that this force here, Fm, the magnetic force, which is equal to QV cross B, this is equal to the mass of the particle divided by centripetal acceleration. Or so it's mass times acceleration, which is centripetal acceleration. So this is equal to what? So mass mv squared over r. So now, like if we solve for r, we get that r is equal to mv squared over qvb, and we're assuming here, we can assume that like in this scenario, v and b are directly perpendicular, so that means that sine theta is equal to 1. And so what this gives us is that r is equal to mv over qb. And so we can solve for the radius of the circle traveled by a charge in a constant magnetic field through this equation. Now if the charge is negative, it would travel in the opposite direction, but it would still have the same radius since none of the magnitudes have changed. From this we can see that r here is directly proportional to mass, and r is directly proportional to velocity, which should make sense. As a more massive particle, you would have more inertia, so it would be harder for it to rotate or to turn in a circle, and a faster particle again has more inertia, it would have more momentum. Again, both of these contribute to more momentum, so it would be harder to turn in a circle. And then we see that r is inversely proportional to charge. So a greater charge will have a greater force, so the circle will be smaller, and r is inversely proportional to magnetic field strength. So if you increase the magnetic field strength, again, the force will be greater, so the circle traveled will have a smaller radius. Okay, and then let's look at another example of applying the Lorentz force. So let's say we have two wires here that are parallel, and then we have a current traveling through both wires. So first, let's say that we have the current traveling through the wires in the same direction. So let's just say they're in the same direction. Okay. Now, if we look at these, we want to see, do these wires attract or repel? Well, they're going to have magnetic field interactions with each other, and we know that the force in one wire is going to be the same as the force on another wire, as the other wire, but in opposite directions because of Newton's third law, when we're assuming that there's no external forces on it. So to find the force between the wires, we can analyze this by first finding the magnetic field created by one of the wires. So let's just say the left wire here, since it has a current going upwards, we can use the right hand rule and see that the circular magnetic field is going to be going into this plane at where the other wire is at. So the magnetic field is going to be going like in this direction, right? So that means that it's going to be going into the plane at this wire. So this wire will be inside of a magnetic field that's since this wire, if we assume it's thin, we can say that this magnetic field is relatively uniform. So if there's a distance r between them, then we know that the magnetic field that this wire, the right wire, experiences from the induced magnetic field in the left wire is going to be equal to, we see B is going to be equal to here, it's equal to mu, mu naught I divided by 2 pi r. So that's the strength of the magnetic field here. And then now, if we want to find the force between them, we can look at the Lorentz force on this right wire based on the so we can find the Lorentz force on this right wire based on the magnetic field created by this left wire. So using the formula for Lorentz force on a current carrying wire, we have that F, the magnetic field, or the magnetic force, is equal to IL cross B, right? And now L, if we look at like a section of the wire, so even if these wires like extend to infinity here, if we find the force on a section of these wires, so let's just say the section here has length L, then the force on this section of wire here is going to be equal to IL, and then we see that these magnetic, or the current, and or at least the length of this wire and the magnetic field is perpendicular, so we can just multiply them together to get the magnitude. And so the force is going to be IL, and then let me label these i's. So let's call the left one I1 and the right one I2. So the left one is the one inducing the magnetic field, so we call the magnetic field strength is I1, and then the Lorentz force uses I2 from this right wire, so this one is I2. So if we substitute this equation for the magnetic field strength in this Lorentz force equation, we get that the force on this right wire is equal to IL mu naught I1, so I2L mu naught I1 over 2 pi r. And so if we rearrange this a bit, we get that this force, the force per length of this wire, so the force over the length of this wire, if we add a delta here, so the force for delta length here is going to be equal to mu naught I1 I2 over 2 pi r. And now if we look at this, we see that since we arbitrarily chose the left wire as the one inducing the field, if we use the right wire instead and do the calculations again, we'll end up with the exact same answer, which fits with Newton's third law, as we know that the action and reaction forces should be equal in magnitude. And so the magnitude of the force per unit length of this wire is going to be equal to mu I1 I2 over 2 pi r. And so that is how you apply like Lorentz force and induced magnetic fields to find the attraction between these two wires. And this is going to be attractive force because if we apply the left hand rule, we see that the current is going upwards and the magnetic field is going into the page, which means that the force on this wire is going to be inwards. And similarly, you can see that the force on this wire is going to be inwards as well, because the induced field from the other wire is going to be going out of the page. So that's for when the current is in the same direction. However, when the current is in the opposite direction, we'll see that the direction of the magnitudes of all the variables didn't change. So this equation for the magnitude of the force per length of the wire is the same, except if the current is in opposite directions, that will flip the force and cause it, or they'll flip the direction of the force, which means that these will instead repel. So if the current is going in opposite directions in parallel wires, the wires will repel, whereas if they're going in the same direction, the wires will attract. All right, thank you very much, and that is an introduction to magnetism and magnetic fields and the Lorentz force.